The fastest object humans have ever launched has been flying away from Earth for nearly 50 years. It has passed every planet. It has crossed into the space between the stars, and it is still not out of the solar system. At the speed it is traveling, about 17 kilometers every second, fast enough to cross from New York to London in roughly 5 minutes, it will need another 30,000 years just to reach the true outer edge of the Sun's domain. We tend to think the solar system ends somewhere past the last planet. It does not. It reaches almost unimaginably farther, and in this video, we are going to travel all the way to the end of it. The object is called Voyager 1. It launched in 1977, before most people watching this were born, and it has been traveling outward ever since, carried by the momentum of a single push given to it when it was young. It is now more than 24 billion kilometers from Earth, so distant that its radio signals, moving at the speed of light, take more than 22 hours to reach us. When engineers on Earth send it a command, they wait the better part of a day for it to arrive, and then nearly another full day to hear whether it worked. It has a twin, Voyager 2, launched the same year and traveling in a different direction, almost as far away. These two machines are the most distant objects our species has ever made, and we will be following them throughout this journey, because they are the only travelers who have actually crossed any of the boundaries we are going looking for. And there are several boundaries. That is the strange thing about the edge of the solar system. It is not a single line. It is not a wall or a shoreline or a cliff that drops away into nothing. Depending on what you measure, the edge of the solar system lies in one of several completely different places, separated by enormous distances. There is the edge marked by the last planet. There is the edge marked by the icy worlds beyond the planets. There is the edge where the wind from the sun finally dies. And there is the edge where the sun's gravity at last lets go, which is so far away that the Voyagers, after half a century, have not traveled even 1% of the distance to it. Each of these is a real edge. Each is defended by serious scientists as the boundary of the solar system. And each one we reach will turn out not to be the end, but a doorway to something farther out. The reason there is no single answer is that the sun holds on to the things around it in more than one way. It holds them with its light, which warms the planets and fades with distance. It holds them with its wind, a constant stream of particles flowing outward in every direction. And it holds them with its gravity, which reaches farther than either light or wind, far enough to keep distant icy worlds in orbit at distances that begin to approach the territory of other stars. Each of these forms of influence fades at a different rate and reaches a different distance. So when we ask where the solar system ends, we are really asking which kind of influence we mean. The light gives one answer, the wind gives another. The gravity gives a third, far more distant than the rest. There is no contradiction in this. The solar system simply has several edges, layered one outside the next, like the faint outer rings of something that never quite stops. In this video, we are going to pass through all of them, one after another, traveling outward from the warmth of the sun into the deep cold beyond. We will follow the Voyagers as far as they have gone, and then we will keep going, into regions no human object will reach for thousands of years. The simple question we are starting with, where does the solar system end, will turn out to have 4 answers, each of them true, each of them stranger than the last. If you find these journeys through the cosmos worthwhile, a like or a subscribe helps us keep making them. Begin with the thing we think we know. When most people picture the solar system, they picture a diagram. The sun at the center glowing yellow. Then the planets, arranged in tidy circles, each at a comfortable distance from the next. Mercury, Venus, Earth, Mars, then a gap, then the giants, Jupiter, Saturn, Uranus, Neptune. The diagram fits neatly on a page. You can take it in at a glance, and it leaves the strong impression that the solar system is a compact, orderly place, with a clear outer rim somewhere just past the last planet. This picture is almost entirely misleading, and the first thing it gets wrong is the distances. In the diagrams, the planets sit close together, evenly spaced, easy to see. In reality, the spacing is nothing like that. If you shrank the Sun down to the size of a basketball and placed it at one end of a field, the Earth would be a grain of sand about 30 paces away. Jupiter would be a small marble more than 150 paces from the Sun. And Neptune, the outermost of the major planets, would be another grain of sand nearly a kilometer away from that basketball. The planets are not crowded together. They are tiny specks separated by vast, almost empty gulfs. The solar system, even the familiar part of it, is mostly emptiness. It is worth dwelling on how counterintuitive this is, because the emptiness only deepens as we travel outward, and it is one of the central facts of this whole journey. We are used to thinking of space as full of things, because the images we see are full of things. Photographs crowded with planets and moons and rings, diagrams packed with orbits. But those images are compressed. They have to be, or the planets would be invisible specks lost in oceans of black. The truth is that if you were placed at a random point inside the solar system and told to look around, the overwhelming probability is that you would see nothing nearby at all. No planet, no moon, no asteroid, just the Sun, a bright point in one direction, and the distant stars in every other. The solar system is not a crowded neighborhood. It is a near-perfect vacuum with a handful of specks scattered through it. And the farther out we go, the more this becomes true. Until in the outermost regions, an object can travel for a human lifetime without coming near anything at all. The second thing the diagram gets wrong is more important for our journey. It implies that the solar system ends at the last planet. For most of human history, this was a reasonable assumption. Neptune, discovered in 1846, was the most distant major planet anyone knew of. It was found in a way that still stands as one of the great triumphs of science, not by chance, but by prediction. Astronomers had noticed that Uranus, the seventh planet, was not moving quite as the laws of gravity said it should. Its orbit was being tugged by something unseen. Two mathematicians, working independently, calculated where an undiscovered eighth planet would have to be to explain the tug, and when astronomers pointed their telescopes at the predicted spot, Neptune was there, almost exactly where the mathematics said it would be. It was a stunning confirmation that the solar system obeyed precise, predictable laws, and that those laws could reveal worlds the eye had never seen. Beyond Neptune, as far as the telescopes of the 19th century could tell, there was nothing. The Sun had 8 planets, and past the 8th, empty space began. The edge of the solar system was simply the orbit of Neptune, a little under 4.5 billion kilometers from the Sun. That was the boundary. That was where our cosmic neighborhood stopped. But it was not the boundary. It was only the first of several, and the easiest one to reach. To understand why the orbit of the last planet is not the edge of the solar system, we have to look more closely at what counts as belonging to the Sun, and we have to be willing to follow the Sun's influence outward into regions that no 19th century astronomer could have seen. Because beyond Neptune, in the cold and the dark, there is far more of the solar system waiting. More worlds, more structure, more distance than the mind comfortably holds. And the Sun's reach, as we will see, extends almost unimaginably farther than the orbit of its outermost planet. Before we go there, it is worth pausing on the planet that, for a while, seemed to be the true edge. Neptune is a world we have visited exactly once. In 1989, the Voyager 2 spacecraft, the same machine still flying through space today, passed close to Neptune and sent back the only detailed photographs we have ever taken of it. They showed a deep blue world, wrapped in the fastest winds in the solar system, winds that howl at more than 2,000 kilometers per hour through an atmosphere far colder than anything on Earth. Neptune is so far from the Sun that it receives about 1,000 times less sunlight than we do. Noon on Neptune is a deep twilight. The Sun, seen from there, is no longer a disk you could not bear to look at. It is a brilliant point, the brightest star in a black sky, casting a pale light across the blue clouds. Neptune also has a moon that hints at what is to come. Its largest moon, Triton, is a strange world that orbits its planet backwards, against the direction of Neptune's spin, which tells astronomers that Triton did not form alongside Neptune, but was captured later, dragged in from the surrounding region by Neptune's gravity. When Voyager 2 flew past, it found that Triton, despite being one of the coldest places in the solar system, with a surface temperature near -235 degrees Celsius, was geologically active. Plumes of nitrogen gas were erupting from its surface, rising kilometers into its thin atmosphere. A world that cold had no business being alive, and yet it was. Triton was a preview, although no one fully understood it at the time, of a lesson the outer solar system would teach again and again. That distance from the sun and bitter cold do not necessarily mean stillness, and that the frozen worlds of the outer dark can hold surprises. From Neptune, the sun is still clearly the master of the sky. But its dominion is fading, and just beyond Neptune, the solar system does something the old diagrams never showed. It keeps going. Having seen where the old boundary was thought to lie, let us now make the journey outward properly, from the warmth of the inner solar system to the cold of its edge, so that the true scale of the thing can build in the mind the way it builds in reality, gradually and then overwhelmingly. We start close to the sun, in the bright, warm, fast-moving region where the Earth orbits, and we travel outward at a steady pace, watching the light fade and the distances grow. Close to the sun, everything happens quickly. The four inner planets, Mercury, Venus, Earth, and Mars, are small worlds made of rock and metal, and they orbit at a brisk pace. Mercury races around the sun in just 88 days. Earth takes a year, the unit of time our whole civilization is built around. These inner planets are close together as solar system distances go, and they are bathed in strong sunlight. This is the part of the solar system that feels familiar and full, the part where the sun is unmistakably in charge, a fierce and dominating presence that lights and warms everything around it. If the solar system were only this, it would be a small and cozy place. But the inner planets occupy only the innermost sliver of the sun's domain, and as soon as we pass the orbit of Mars, the character of the journey changes. Beyond Mars, we enter the asteroid belt, and here the popular imagination and the reality part company completely. In films and in stories, the asteroid belt is a crowded, dangerous place, a churning swarm of tumbling rocks packed so tightly that a pilot must weave frantically between them to avoid being crushed. This image is almost the exact opposite of the truth. The asteroid belt is one of the emptiest places imaginable. It does contain a great many objects, more than 1 million asteroids large enough to track, and countless smaller ones. But they are spread across such an enormous volume of space that the average distance between them is hundreds of thousands, sometimes millions of kilometers. If you were standing on one asteroid, the nearest neighbor would, in almost every case, be far too distant to see as anything more than a faint point of light, if you could see it at all. Every spacecraft we have ever sent through the asteroid belt, and there have been many on their way to the outer planets, has passed through it without the slightest danger. To deliberately fly a spacecraft close enough to photograph a single asteroid, mission planners have to aim carefully and adjust the trajectory, because the odds of drifting near one by chance are so small as to be negligible. The asteroid belt is not a barrier. It is a vast, sparse scattering of debris, the leftover rubble of a planet that never formed, prevented from gathering together by the immense gravity of Jupiter pulling at it from beyond. The total mass of everything in the asteroid belt, all those millions of objects combined, adds up to less than the mass of the Moon. It is less a belt than a rumor of one, spread thin across a gulf of space, larger than the entire region occupied by the inner planets. The largest object in the asteroid belt, Ceres, is round enough and large enough to be classified, like Pluto, as a dwarf planet. It is about 940 kilometers across, and when the Dawn spacecraft orbited it in 2015, it found a surprisingly complex little world with bright deposits of salt on its surface that may have welled up from a briny layer beneath the crust. Even here, in the inner solar system's scrapyard, there are worlds with histories and secrets. But Ceres is the exception. Most of the asteroid belt is empty space, and crossing it teaches the first real lesson of the outward journey: that the solar system is far emptier and far larger than any diagram can show. The crossing from the orbit of Mars to the orbit of Jupiter is a vast, slow traverse through near total emptiness, and it is only the beginning. Beyond the asteroid belt, the distances take a sudden leap, and we arrive at the gas giants, Jupiter and Saturn, followed much farther out by Uranus and Neptune. These are worlds of a completely different kind from the small rocky planets of the inner system. They are enormous. Jupiter alone is more massive than all the other planets in the solar system combined, more than twice over. You could fit more than 1,000 Earths inside it. It is not a world with a surface you could stand on. It is a vast ball of gas and liquid, wrapped in bands of cloud and stirred by storms larger than entire planets. The most famous of these storms, the Great Red Spot, is a hurricane that has been raging for centuries, wide enough to swallow the Earth whole. Jupiter is so massive that its gravity shapes the entire solar system around it. It governs the asteroid belt, holding it in place and preventing it from coalescing. It captures comets and flings them onto new paths. It has, over the history of the solar system, acted as a kind of gravitational shield for the inner planets, deflecting or absorbing objects that might otherwise have struck the Earth. And it commands a system of moons so large and varied that it is almost a miniature solar system in itself. Jupiter has at least 95 known moons, 4 of which are large worlds in their own right. Io, the most volcanically active body in the solar system, its surface constantly remade by eruptions. Europa, wrapped in a shell of ice beneath which lies a global ocean of liquid water, one of the most promising places in the solar system to search for life. Ganymede, the largest moon in the solar system, bigger than the planet Mercury. And Callisto, a heavily cratered world that preserves a record of the solar system's violent youth. When we look at Jupiter and its moons, we are not looking at a single object. We are looking at a complex, interconnected system, held together by the giant's overwhelming gravity. Farther out lies Saturn, the second of the giants and the most beautiful object in the solar system. Saturn's rings are made of countless particles of ice and rock, ranging in size from grains of dust to boulders, all orbiting the planet in a vast flat disk that spans hundreds of thousands of kilometers, yet is, in places, only about 10 meters thick. From a distance, the rings look solid and smooth. Up close, they are a swirling, dynamic structure, shaped and shepherded by the gravity of Saturn's moons, full of waves and gaps and intricate detail. The rings will not last forever. They are slowly raining down into Saturn's atmosphere, and in perhaps a few 100 million years, they may be gone entirely. We are living at a fortunate moment, when the most spectacular ring system in the solar system happens to exist for us to see. Saturn, too, has a remarkable family of moons. The largest, Titan, is bigger than Mercury, and is the only moon in the solar system with a thick atmosphere, denser even than Earth's. Beneath that hazy orange atmosphere, Titan has a landscape that is eerily Earth-like and utterly alien at the same time. Rivers, lakes, and seas, complete with rainfall and erosion and shorelines. except that the rain is not water but liquid methane, falling from methane clouds onto a frozen surface where water ice is as hard as rock. The Cassini spacecraft, which orbited Saturn for 13 years, dropped a small probe called Huygens onto Titan's surface in 2005, the most distant landing humanity has ever achieved. It sent back images of a dim orange world, with rounded pebbles of ice scattered across a damp plain, under a sky the color of weak tea. Another of Saturn's moons, Enceladus, small and bright and covered in fresh ice, was found by Cassini to be spraying enormous plumes of water vapor into space from cracks near its south pole, fed by a hidden ocean beneath its crust. Like Triton at Neptune, like Europa at Jupiter, Enceladus was another reminder that warmth and water and activity can be found in the most unexpected places, far from the sun, in worlds that by every expectation should have been frozen dead. Beyond Saturn, the distances grow vast, almost beyond comprehension, and we reach Uranus and Neptune, the two outermost giants, worlds of pale blue and deep blue, far colder and far more remote than Jupiter and Saturn. These are sometimes called ice giants because beneath their atmospheres, they are thought to contain large amounts of water, ammonia, and methane in exotic high-pressure states. They are the least explored of the major planets. Each has been visited only once by Voyager 2 in the 1980s, and we have seen them up close on only those two brief occasions. Uranus is strange even among the giants. It is tipped over on its side, rotating almost at a right angle to the plane of its orbit, so that its poles, rather than its equator, take turns facing the sun. The cause was probably an enormous collision in the distant past, a blow large enough to knock an entire planet onto its side. It is worth lingering for a moment on how slowly time itself seems to pass out among the giant planets, because it is part of what makes the outer solar system feel so different from our own. On Earth, a year is a familiar thing, a single trip around the sun, marked by the turning of the seasons. But the giant planets take far longer to make that trip. Jupiter takes nearly 12 Earth years to orbit the sun once. Saturn takes almost 30. Uranus takes 84 years, a full human lifetime, so that a person born when Uranus was in one part of its orbit might live their entire life and never see it return to where it started. And Neptune takes about 165 years, which means that since its discovery in the 19th century, it has completed only a single orbit of the Sun, returning in 2011 to roughly the position where it was first found. A year on Neptune is longer than the entire history of its study by human astronomers. Out here, the clock of the solar system runs slow, and the farther out we go, the slower it runs, until in the Oort Cloud, a single orbit can take longer than the time that has passed since the first human beings walked the Earth. By the time we reach this part of the solar system, the sun has become a small thing in the sky, and its light is thin and pale. The journey from Jupiter to Neptune crosses a gulf so wide that sunlight, traveling at 300,000 kilometers per second, takes hours to span it. And yet, for all its vastness, this is still only the familiar part of the solar system, the part with planets, the part that fits on the old diagrams. We have traveled from the warm inner system, across the empty belt, past the great giants and their systems of moons, all the way to the orbit of the outermost planet. Think about what that fading of light really means as we travel. On Earth, the sun is overwhelming, too bright to look at, the source of every shadow and every color we see. By the time we reach Jupiter, sunlight has weakened to a small fraction of what we know. And a human standing there. Could they stand there at all? Would find the sun shrunk to a brilliant but much smaller disk. By Saturn, the light is fainter still. By the time we reach Neptune and the Kuiper Belt, the sun has dwindled to little more than an extraordinarily bright star, casting a pale light in which a human eye would see the surrounding worlds only dimly, as if by strong moonlight. And out in the Oort Cloud, the sun would be merely the brightest star in a sky full of stars, not obviously different from the others, except in its brilliance, no longer a source of warmth at all, just one more point of light among the countless points that fill the dark. This is the journey of the light, from a blinding presence that rules the sky, to a warm companion, to a distant star, to a single bright point lost among the constellations. The fading of the sun is, in its own way, the truest measure of the distances we have crossed. And we have only just arrived at the place where the old maps end and the real strangeness begins. Because just beyond Neptune, the solar system opens into a region the old astronomers never knew. A broad ring of frozen worlds that more than doubles the size of everything we have traveled so far. Just beyond Neptune, the solar system reveals the first of its hidden layers. For most of the 20th century, astronomers suspected something might be out there, but they could not prove it. The telescopes were not good enough. The objects, if they existed, would be small, dark, and impossibly far away, reflecting only the faintest trace of sunlight back toward Earth. Finding them was like trying to spot a lump of coal at the far end of a dark valley by the light of a distant street lamp. It was not until 1992 that the first one was found, after years of patient searching by two astronomers, David Jewett and Jane Liu, who had scanned the sky night after night looking for something that most of their colleagues doubted was there. The object they found was small, only a couple of 100 kilometers across, orbiting far beyond Neptune in the cold dark. Within a few years, astronomers had found dozens more, then hundreds. Today we know of thousands, and we believe there are hundreds of thousands more waiting to be discovered. They form a vast ring of frozen worlds encircling the entire solar system, far beyond the last planet. We call it the Kuiper Belt. The Kuiper Belt is named after Gerard Kuiper, an astronomer who, in the 1950s, was one of several scientists to suggest that the region beyond Neptune might not be empty. He reasoned that when the solar system formed, the same process that built the planets should have left behind a great deal of leftover material in the outer reaches, too spread out and too far from the sun to gather into large worlds. That leftover material, frozen and preserved in the deep cold, should still be out there. He turned out to be right, although the details of his prediction were not exactly correct, and he did not live to see the belt confirmed. The structure is essentially the kind of thing he imagined. A broad disk of icy bodies beginning around the orbit of Neptune and extending outward billions of kilometers farther, made of the debris from which the planets were assembled 4.5 billion years ago. To understand the Kuiper Belt, it helps to think of it as a kind of frozen archive. The objects in it are ancient, formed in the earliest days of the solar system and largely unchanged since. They are too far from the sun to have been warmed, melted, or reshaped. They simply drift slowly along their enormous orbits, preserving in their ice and rock a record of the conditions in which the planets were born. Closer to the sun, the original material of the early solar system has been cooked, melted, churned, and recycled again and again by heat and collisions and geological activity. The rocks of the Earth have been through this mill so many times that almost nothing of the original material survives in its first form. But out in the Kuiper Belt, in the deep cold, far from the sun's heat and far from the crowding that drives collisions, the early material has been left almost untouched. When we study a Kuiper Belt object, we are looking at a sample of the original substance of the solar system, kept in cold storage for longer than there has been life on Earth. This is part of why these distant worlds matter so much to scientists. They are not just remote curiosities. They are the surviving evidence of how everything began, the pages of the solar system's first chapter, preserved because nothing out there was warm enough or crowded enough to destroy them. The most famous resident of the Kuiper Belt is one you have known since childhood, although you may not have known it lived there. Pluto, discovered in 1930 by a young American astronomer named Clyde Tombaugh, was for 76 years considered the 9th planet of the solar system. Tombaugh found it by painstakingly comparing photographs of the same patch of sky taken on different nights, looking for the single point of light that had shifted position against the fixed background of stars. It was grueling, eye-straining work, and when he found the faint moving dot, it was hailed as the discovery of a new planet, the first found by an American, and the most distant world then known. Generations of schoolchildren learned its name as the last in the line, the small cold world at the far edge of everything. But as astronomers began to find more and more objects in the Kuiper Belt, a problem emerged. Pluto was not alone out there. It was one of many, and some of the newly discovered objects were nearly as large as Pluto itself. The turning point came in 2005, when a team of astronomers led by Mike Brown discovered an object even farther out than Pluto, in the cold reaches beyond the main Kuiper Belt. They named it Eris, after the Greek goddess of discord, and the name proved fitting. Eris appeared at first to be larger than Pluto, and it was certainly more massive, about 27% heavier. This created an awkward question. If Pluto was a planet, then Eris had to be a planet too. And if Eris was a planet, then so were the other large objects being found in the Kuiper Belt, and so would be the many more that were surely waiting to be discovered. The solar system might have 10 planets, or 20, or 50. The tidy list of 9 was no longer tenable. Brown, who would later cheerfully describe himself as the man who killed Pluto, had forced the issue. Either the solar system had to admit a swelling crowd of new planets, or it had to rethink what the word planet meant. In 2006, the International Astronomical Union, the body responsible for naming and classifying objects in space, met in Prague to resolve the question. After a contentious debate, they produced a new definition of the word planet. To be a planet, an object had to do 3 things. It had to orbit the sun, it had to be large enough for its own gravity to pull it into a round shape, and it had to have cleared its orbital neighborhood of other objects. Pluto met the first 2 conditions, but failed the third. It shares its region of space with countless other Kuiper Belt objects, rather than having swept its path clean the way the 8 major planets have. By the new definition, Pluto was not a planet. It was reclassified as a dwarf planet, along with Eris and several other large round objects in the outer solar system. The solar system was back to 8 planets, and Pluto, after 76 years, was demoted. The decision was, and remains, controversial. Many people felt a genuine sense of loss, as though a familiar friend had been taken away. There were protests, petitions, and a great deal of public affection for the little world that had been struck from the list. Some astronomers disagreed with the new definition on scientific grounds, arguing that the requirement to clear one's orbit was poorly defined and arbitrary, and that by a strict reading, even Earth and Jupiter have not entirely cleared their paths. The debate has never fully settled, and there are respected planetary scientists today who still refuse to accept the demotion. But the reclassification of Pluto, whatever one thinks of it, reflected a real and important discovery. That beyond Neptune lies not a single small planet, but an entire population of icy worlds, a whole region of the solar system that the old picture had completely missed. Pluto was not demoted because it had shrunk or changed. It was reclassified because the solar system had turned out to be far larger and more crowded in its outer reaches than anyone had realized. The demotion was, in a sense, a measure of how much we had learned. Pluto was not the only large dwarf planet to emerge from the Kuiper Belt. There is Makemake, a bright, icy world a little smaller than Pluto, named after a creation deity of the Rapa Nui people of Easter Island. There is Haumea, one of the strangest objects in the solar system, an egg-shaped world spinning so fast, completing a full rotation in under 4 hours, that its own rotation has stretched it into an elongated shape, and which has a ring of its own and 2 small moons. There is Quaoar, and Orcus and Gongong, each a frozen world hundreds of kilometers across, each named after a deity from one of the world's mythologies, each utterly unknown to science a generation ago. These are not minor pieces of debris. They are substantial worlds, some with moons, some with thin atmospheres that freeze and thaw as their orbits carry them nearer to and farther from the Sun. The Kuiper Belt is not a belt of rubble. It is a belt of worlds, a whole class of planets that we simply had not been able to see until our telescopes grew sharp enough to find them. The Kuiper Belt is not a uniform ring. The more astronomers have studied it, the more structure they have found within it. And that structure tells a story about the history of the whole solar system. Some of the objects in the belt follow neat, nearly circular orbits, lying flat in roughly the same plane as the planets. And these are thought to have formed more or less where they are now, and to have been left undisturbed ever since. Astronomers call them the cold classical objects, not because they are colder than the rest, but because their orbits are calm, gentle, and unhurried, never having been stirred up by the gravity of a passing planet. These are the most pristine objects in the solar system, the least altered material left anywhere, drifting in the same quiet paths they have held since the beginning. Arakoth, the little snowman-shaped world that New Horizons visited, is one of them, which is exactly why it was so valuable to study. It is a piece of the original solar system, preserved in its original place. Other objects in the belt tell a more turbulent story. Many of them, including Pluto itself, are locked into a precise rhythm with Neptune, a relationship astronomers call a resonance. Pluto orbits the Sun exactly twice in the time it takes Neptune to orbit 3 times, a steady 2-for-3 beat that is held for billions of years. This is not a coincidence. It is a gravitational lock, a kind of cosmic gearing, and it protects Pluto from ever colliding with Neptune, even though their orbits cross, because the rhythm ensures the two worlds are never near the crossing point at the same time. There are so many objects sharing this particular 2-for-3 rhythm with Neptune that astronomers have given them a collective name. They are called the Plutinos, the little Plutos, after the most famous member of their group. Their existence is a clue to the solar system's distant past, evidence that Neptune did not form where it now orbits, but drifted outward in the early days, sweeping up countless icy bodies and locking them into step with it as it migrated, like a snowplow, gathering a bank of snow ahead of its blade. Pluto itself, when New Horizons finally reached it, turned out not to be a single world at all, but the center of a miniature system. It has 5 moons, and the largest of them, Charon, is so big in proportion to Pluto, more than half its width, that the two do not simply orbit as a planet and its satellite. Instead, they orbit a shared point in the empty space between them, both worlds circling that invisible balance point like 2 dancers swinging around their joined hands. Pluto and Charon are, in effect, a double world, a binary system of 2 icy bodies locked face to face, each forever showing the same side to the other, turning together through the dark. Charon is a remarkable world in its own right, with a vast canyon system stretching across its surface, and a strange dark red cap at its north pole, thought to be a stain of material that drifted over from Pluto's thin atmosphere, and was slowly baked into color by billions of years of faint sunlight. Around this central pair orbit the 4 smaller moons, tiny irregular bodies with names drawn from the mythology of the underworld: Styx, Nyx, Kerberos, and Hydra, after the river and the creatures that guard the realm of the dead, a fitting set of names for the attendants of a world named after the lord of that realm. These small moons tumble chaotically as they orbit, never settling into a steady spin, turning end over end in the complex gravitational tug of the double world at their center. All of this, an entire system of 5 moons and a double world and a precise gravitational rhythm with Neptune, exists in a region that, a single human lifetime ago, was thought to contain nothing but 1 small distant planet, if that. The Kuiper Belt has turned out to be not a barren outer fringe, but a complex, structured, populated region, full of worlds with their own moons and histories and relationships, a whole second solar system of ice beyond the solar system of rock and gas we thought we knew. And it was all hidden, all of it, simply because it was too faint and too far to see, until our instruments grew sharp enough to reveal it. For most of the time since its discovery, Pluto itself was little more than a blurry point of light, even in the best telescopes. We knew its size only approximately. We knew almost nothing about its surface. Even the Hubble Space Telescope could resolve it only as a fuzzy, mottled disk, a few indistinct patches of light and dark. That changed in 2015, when a spacecraft called New Horizons, after a journey of 9.5 years and nearly 5 billion kilometers, flew past Pluto and sent back the first close-up images ever taken of it. The spacecraft had been launched in 2006, the same year Pluto was demoted, so that it set out to visit the 9th planet and arrived at a dwarf planet, the definition having changed beneath it while it was in flight. What it found, when it arrived, astonished everyone. Pluto was not the dead, cratered ball of ice that many had expected. It was a world of startling complexity. It had mountains of frozen water ice, some of them thousands of meters tall, as high as the Rockies. It had vast, smooth plains, free of craters, which meant they were geologically young, resurfaced by some process still at work. It had what appeared to be glaciers, slowly flowing across the surface. It had a thin blue atmosphere, hazy and layered, which the spacecraft photographed glowing softly as it looked back at Pluto with the sun behind it. It had a surface marked with a huge, pale, heart-shaped region that quickly captured the public imagination. On a world so far from the sun that sunlight is 1,000 times fainter than on Earth, where the temperature hovers around -230 degrees Celsius, something was keeping Pluto geologically alive. The left lobe of that famous heart, a vast smooth plain informally named Sputnik Planitia, became the most studied feature on the entire world. It is a great basin filled with frozen nitrogen, and its surface is divided into enormous polygonal cells, each tens of kilometers across, fitted together like the panes of a stained glass window, or the cracked surface of dried mud seen from above. These cells are the surface expression of slow convection. The frozen nitrogen, warmed very slightly from below by the faint internal heat of the world, churns and overturns over millions of years, the way a thick liquid does when heated gently from beneath, erasing craters and constantly renewing the surface. A world that should have been frozen solid and geologically dead was instead slowly turning itself over, at the lowest imaginable rate, in the deep cold, billions of kilometers from the sun. No one had predicted this. The discovery transformed our understanding of what distant, cold worlds could be. Being far from the sun, it turned out, did not necessarily mean being dead. It was the lesson of Triton and Enceladus once again, written this time on the surface of the world that had defined the edge of the solar system for 3 generations of schoolchildren. New Horizons did not stop at Pluto. It had crossed the solar system too fast to slow down and stay. So after the flyby, it continued onward, deeper into the Kuiper Belt, and the mission team searched for another object it could reach. In the first hours of 2019, the spacecraft flew past a second, much smaller object, a body about 36 kilometers long, more than 1.5 billion kilometers beyond Pluto. It is now called Arrokoth, a word meaning sky in the Powhatan language. Arrokoth turned out to be one of the most important objects we have ever visited, precisely because it is so small and so undisturbed. It is shaped like 2 rounded lobes joined together, like a flattened snowman or 2 pancakes stuck end to end, and its structure preserves a record of how the building blocks of planets first came together. Arrokoth appears to have formed gently, when 2 separate objects, orbiting close to one another, drifted together slowly and stuck, rather than colliding violently. The discovery supported the idea that planets are built not by violent high-speed smash-ups, but by the gentle accumulation of nearby material, clumping together softly over time. Arakoth is a fossil of the earliest stage of planet formation, frozen and untouched for 4.5 billion years, and we have seen it up close. It remains to this day the most distant object any spacecraft has ever visited. So the Kuiper Belt gives us our second candidate for the edge of the solar system. It is a real boundary in a meaningful sense. It marks the outer limit of the region where the solar system's leftover building material gathered into a recognizable disc-shaped structure. The main, densest part of the belt ends rather abruptly around 50 times the distance from the Earth to the Sun, a fall-off so sharp that astronomers once called it the Kuiper Cliff, after which the population of objects drops away dramatically. If you wanted to say that the solar system ends where its planet-forming disk ends, you could draw the line here, at the outer edge of the Kuiper Belt, several billion kilometers beyond Neptune. Many people do. It is a defensible answer, and it is far more distant than the orbit of the last planet, the answer the 19th century would have given. But this edge, too, fails to be the final one, and for a reason that has nothing to do with icy worlds or leftover debris. Because while the Kuiper Belt marks the outer limit of the solar system's solid material, the Sun itself extends far beyond it, not in the form of rock and ice, but in the form of something invisible, something streaming outward from the Sun in every direction at over 1 million kilometers per hour. The Sun is not just a source of light and gravity. It is a source of wind. And that wind blows far past the Kuiper Belt, carving out a vast bubble in the surrounding galaxy, a bubble whose boundary is the next edge of the solar system we are going to reach. It is the edge that the Voyagers actually crossed. To find the third edge of the solar system, we have to stop thinking about the Sun as a ball of light, and start thinking about it as something that is constantly leaking. The Sun is not a sealed object with a clean surface. It is a churning sphere of superheated gas, so hot that its outer layers are continuously boiling off into space. From the top of the Sun's atmosphere, a steady stream of charged particles, mostly protons and electrons, flows outward in every direction. This stream is called the solar wind, and it never stops. Every second, the Sun sheds about 1 million tons of material into space in this way, flinging it outward at speeds of more than 1 million kilometers per hour. The Sun has been doing this for 4.5 billion years, and it will continue for billions more, a constant exhalation of itself into the surrounding dark. We can see the effects of this wind much closer to home. When the solar wind sweeps past the Earth, it is mostly deflected by our planet's magnetic field, but some of it leaks in near the poles, and when those particles strike the upper atmosphere, they make it glow. That glow is the aurora, the northern and southern lights, the shimmering curtains of green and red that appear in the polar skies. Every time you see a photograph of the aurora, you are looking at the solar wind made visible, the Sun's outflowing breath crashing into the top of our atmosphere. The same wind that paints those lights in the sky is the wind that, far beyond the planets, carves out the boundary of the solar system. It is a single phenomenon, gentle and beautiful where it meets the Earth, and vast and structural where it meets the edge of interstellar space. The solar wind does not simply fade away as it travels. It keeps going, blowing outward past Mercury, past Earth, past the asteroid belt, past Jupiter and Saturn, past Neptune, past the Kuiper Belt. As it goes, it carves out an enormous bubble in the surrounding space, a vast region dominated by the Sun's wind, rather than by the thin gas that fills the space between the stars. This bubble has a name. It is called the heliosphere, from the Greek word for the Sun, and it is, in a real sense, the true extent of the Sun's physical presence. Everything inside the heliosphere is bathed in material that came from the Sun. Everything outside it belongs to interstellar space, the realm between the stars. The boundary between the two is one of the most meaningful edges the solar system has, because it is the edge of the Sun's own substance, the limit of the territory the Sun fills with itself. The heliosphere is not a perfect sphere, despite its name. the solar system is not sitting still. It is moving through the galaxy, orbiting the center of the Milky Way at about 220 kilometers per second. And as it moves, it pushes through the thin gas of interstellar space. This gives the heliosphere a shape something like a vast, elongated bubble, rounded and compressed on the side facing the direction of travel, and possibly drawn out into a long tail on the side behind, rather like the shape of a comet, or the bow wave and wake of a ship moving through water. The exact shape of the tail is still debated, because we have never been able to see the heliosphere from the outside. We are inside it, and mapping its form from within is like trying to draw the outline of a house while standing in one of its rooms. But the broad picture is clear enough. We are sailing through the galaxy inside a bubble of our own sun's making, and the bubble is shaped by the passage, swept back by the motion the way a windsock is shaped by the breeze. The scale of the heliosphere is difficult to grasp. Its boundary lies roughly 4 times farther from the Sun than Neptune, more than 90 times the distance from the Earth to the Sun. To put that in human terms, light, which crosses from the Sun to the Earth in about 8 minutes, takes around 17 hours to reach the edge of the heliosphere. The bubble is so large that the entire familiar solar system, all 8 planets and the whole Kuiper Belt, sits deep within its inner regions, like a few specks of dust suspended near the center of an enormous balloon. And yet, as we will see, even this vast bubble is small compared to the final edge that lies beyond it. The heliosphere is enormous by the standards of the planets, and tiny by the standards of the Sun's full gravitational reach. As the solar wind travels outward, it gradually slows down, and at a certain distance, something dramatic happens to it. Out there, billions of kilometers beyond the planets, the solar wind runs into the resistance of the interstellar gas pressing back against it. The wind, which has been blowing outward faster than the speed at which disturbances can travel through it, is suddenly forced to slow down. The result is a kind of standing shockwave, a place where the solar wind abruptly piles up, heats up, and slows. This is called the termination shock, and it is the first of 2 boundaries that together make up the edge of the heliosphere. It is, in a sense, the place where the Sun's wind first begins to lose its battle with the galaxy beyond. Crossing the termination shock is the first sign that a traveler is approaching the true edge of the Sun's domain. Beyond the termination shock lies a turbulent region called the heliosheath, where the slowed solar wind churns and mixes, no longer flowing smoothly outward, but piling up and turning aside as it meets the interstellar gas beyond. This is a strange, restless frontier zone, a region of eddies and shifting magnetic fields, where the material of the Sun and the material of the galaxy press against each other, and neither fully gives way. And beyond the heliosheath lies the final boundary, the place where the solar wind finally stops altogether, where the last of the Sun's outflowing material meets the gas of interstellar space and can push no farther. This is the heliopause. It is the outermost edge of the heliosphere, the membrane of the great bubble, the place where the Sun's wind ends and the wind between the stars begins. By the definition that many scientists prefer, the heliopause is the true edge of the solar system, the boundary of the region dominated by the Sun's own material. Cross it, and you are, physically, in interstellar space. The heliosphere is not only a boundary, it is also a shield, and understanding what it shields us from reveals why this particular edge matters for life itself. The galaxy is filled with cosmic rays, which, despite their name, are not rays at all, but particles. Atomic fragments, mostly the bare nuclei of atoms, accelerated to almost the speed of light by violent events scattered across the galaxy, by exploding stars and the spinning remnants they leave behind. These particles travel through interstellar space in every direction, a constant sleet of high-energy radiation washing through the galaxy. When they strike living tissue, they can damage it, breaking apart the molecules of life. And in large enough doses, they are lethal. The space between the stars is bathed in this radiation. It is one of the things that makes deep space so hostile. The heliosphere holds much of it back. As the solar wind streams outward and fills the great bubble, it carries the sun's magnetic field with it, woven through the flowing particles, and this vast magnetic structure deflects a large fraction of the incoming cosmic rays before they can reach the inner solar system. The bubble acts like an enormous weather system, a magnetic cocoon that turns aside the harshest radiation of the galaxy. Without it, the surface of every planet, including the Earth, would be exposed to significantly more cosmic radiation than it is. The Earth has its own magnetic field and its thick atmosphere as additional shields, layers of protection nested one inside another. But the heliosphere is the outermost of them, the first line of defense, the wall of the sun's own making that surrounds everything. When astronomers measured the jump in cosmic rays as the Voyagers crossed the heliopause, they were measuring exactly this. The radiation that the bubble keeps out, suddenly arriving in full force the moment the spacecraft pass beyond the shield. Inside the heliopause, the cosmic ray count was lower, the sun's magnetic field still doing its work. Outside, in true interstellar space, the count rose sharply because there was no longer any shield at all. This raises a question that is easy to overlook. What is interstellar space actually like, the space just on the far side of the heliopause, where the Voyagers are now? It is not truly empty, although it is emptier than almost anything we can imagine. It is filled with a thin gas, mostly hydrogen, left over from the formation of the galaxy and enriched over billions of years by the material thrown off by dying stars. This gas is unimaginably sparse, far thinner than the best vacuum ever produced in a laboratory on Earth, with only a handful of atoms in each small volume of space. But it is there, and it is different from the material inside the heliosphere. It is colder, in a sense, and denser than the thinned-out solar wind at the edge of the bubble, which is one of the ways the Voyagers knew they had crossed over. The instruments detected the change in the surrounding gas, the shift from the sun's sparse, fast wind to the galaxy's slightly thicker, slower medium. The solar system, it turns out, is currently drifting through a particular wisp of this interstellar gas, a region astronomers call the local interstellar cloud, a faint clot of slightly denser material that the sun happens to be passing through at this point in its long orbit around the galaxy. In a few thousand years, the sun will drift out of this cloud and into another region, and the conditions just outside the heliosphere will slowly change, as they have changed many times over the sun's long history. The shape and size of the heliosphere are not fixed either. They depend on the strength of the solar wind, which rises and falls with the sun's activity over an 11-year cycle, and on the density of the interstellar gas the sun happens to be moving through. When the sun is more active, the wind blows harder and the bubble swells outward. When the sun is quieter, the wind weakens and the bubble contracts, and the heliopause draws inward. The boundary of the solar system, by this third definition, is not a fixed line at all, but a breathing, shifting surface, swelling and shrinking with the sun's moods, pushing out into the galaxy and drawing back again over the years and the centuries. The Voyagers, having crossed it, may in principle find it sweeping back over them again if the sun grows quiet enough, the boundary of the solar system washing back and forth across them like a tide line on a beach. It is a strange thought that the edge of the solar system is not only unclear in its definition, but genuinely mobile, a living boundary that moves. For most of history, the heliopause was a theoretical idea, a boundary calculated and modeled, but never seen, never touched, never measured directly. Scientists knew it had to be out there somewhere, but they could only estimate its distance, and the estimates varied widely. There was no way to know for certain what the edge of the heliosphere was really like until something actually reached it, and sent back word. Before the Voyagers, there were the pioneers. It is easy to forget them now, because the Voyagers went farther and lasted longer and captured the public imagination. But the first spacecraft to make the journey toward the outer solar system were two earlier, simpler machines, Pioneer 10 and Pioneer 11, launched in 1972 and 1973, a few years ahead of their more famous successors. They were true pioneers, in the full sense of the word. No spacecraft had ever crossed the asteroid belt before Pioneer 10, and there was real worry before it set out that the belt might be dense enough to destroy it. It was not, of course. The belt is mostly emptiness, as we have seen, and Pioneer 10 sailed through without trouble, proving the route safe for everything that came after. It then became the first spacecraft ever to reach Jupiter, sending back the first close-up images of the giant planet before continuing outward. Pioneer 11 followed, flew past Jupiter, and went on to make the first ever flyby of Saturn, scouting the path that Voyager would later take. Like the Voyagers, the Pioneers were not designed to last. Their missions to the planets were expected to take a few years. And like the Voyagers, they vastly outlived their purpose, flying on past the planets and out toward the edge of the solar system, sending back data for decades. Each of them, too, carried a message, although a simpler one than the Voyager's golden records. Bolted to the side of each Pioneer was a small gold anodized metal plaque engraved with a diagram. It showed the figures of a man and a woman, drawn in simple lines, standing beside an outline of the spacecraft for scale. It showed the position of the Sun relative to a set of distant cosmic landmarks, a kind of map that might, in principle, allow a finder to locate the spacecraft's origin. And it showed the Sun's place among the planets, with a small line tracing Pioneer's path outward from the third world. It was humanity's first attempt to send a message to the stars, a calling card engraved in metal, designed to survive for hundreds of millions of years in the emptiness of space. The golden records that the Voyagers would later carry were a richer, more ambitious version of the same impulse, the desire to say, to whatever might one day find these machines, that we existed, and that we made them, and that we wondered who else might be out there. But the Pioneer's story has a quieter and sadder ending than the Voyager's, and it is one worth telling, because it is the ending the Voyagers are approaching too. The Pioneers were less powerful than the Voyagers, with weaker transmitters and smaller power supplies, and they fell silent sooner. The last faint signal from Pioneer 10 was received in 2003, when it was about 12 billion kilometers from Earth. Engineers listened for it again afterwards and heard nothing. Its power had finally dropped too low for its voice to reach us. Pioneer 11 had gone silent even earlier, in the mid-1990s. And so, for more than 2 decades now, these two trailblazing machines have been drifting onward in total silence, dead and dark, no longer sending anything, no longer heard. They are still out there. Pioneer 10 is heading in the general direction of the bright star Aldebaran, in the constellation Taurus, and if nothing disturbs it, it will take more than 2 million years to get there. Pioneer 11 is heading the opposite way, toward the center of the galaxy. Neither will ever be heard from again. They are ghosts now, coasting outward on the momentum of launches that happened more than half a century ago, carrying their engraved plaques toward stars they will not reach for longer than our species has existed. The Pioneers are a glimpse of the Voyager's future. The Voyagers are still speaking to us, for now, but they will not be for much longer. And when their voices fade, they will join the Pioneers in the silent company of human machines drifting dead through the outer dark. There are by now a small handful of these. Beyond the Pioneers and the Voyagers, the New Horizons spacecraft that visited Pluto is also on an outbound path, still working for the present, but destined eventually to fall silent and drift on. These few machines are the only physical things our species has ever sent toward the edge of the solar system and beyond. Most of them are already silent. The rest soon will be. And all of them, speaking or not, are continuing outward, carrying their plaques and their records and their fading instruments toward the boundaries we are tracing in this video. The slowest and longest expedition humanity has ever undertaken, conducted by machines that will outlast everything else we have ever built. That changed because of the two machines we have been following since the beginning of this journey. The Voyager spacecraft, launched in 1977, were built to study the outer planets, and they did so spectacularly, sending back the first close images of Jupiter, Saturn, Uranus, and Neptune. Their planetary mission was a triumph in its own right. But the engineers who built them had given them more than enough power and durability to keep working after the planets were behind them, and so, after their planetary work was done, they kept going, outward, on trajectories that carried them toward the edge of the heliosphere. And because they were still working, still transmitting, decades after launch, they became the first objects in history to reach and cross the boundary of the Sun's domain. Voyager 1 crossed the termination shock in 2004, and Voyager 2 followed in 2007 in a different direction. They sent back the first direct measurements ever made of that turbulent region, confirming much of what the models had predicted, and surprising scientists with much that they had not. The models, it turned out, had got some things wrong. The real boundary was more complex, more dynamic than the calculations had suggested. This is what happens when a theoretical idea is finally reached and measured directly. The reality is always richer than the prediction. Then, in August of 2012, Voyager 1 crossed the heliopause itself. The moment was unmistakable in the data. The spacecraft's instruments recorded a sudden change. The warm, thin solar wind that had surrounded it for 35 years abruptly gave way to the colder, denser gas of interstellar space. The number of solar particles dropped sharply, and the number of cosmic rays, the high-energy particles from the wider galaxy that are normally partly held back by the heliosphere, jumped up. Voyager 1 had left the bubble. For the first time, a human-made object was outside the heliosphere in the space between the stars. There was no wall, no barrier, no visible line. The spacecraft did not strike anything or pass through any membrane it could feel. The crossing was detected only by the change in the particles around it, the shift from the sun's wind to the galaxy's gas. It took scientists many months of careful analysis to be sure it had even happened, because the change, though real, was not the dramatic event some had imagined. There was no fanfare out there at the edge of the solar system, no marker, no sense of arrival. There was only a quiet, measurable change in the surrounding sea of particles, registered by an instrument on a small spacecraft, and radioed back across billions of kilometers to a planet where more than 17 hours later, a group of scientists studied the numbers and slowly realized what they were looking at. Voyager 2 made the same crossing in 2018 in its different direction, and confirmed the boundary independently, giving us two measurements of the edge of the heliosphere in two different places. The two spacecraft had given humanity its first direct contact with the edge of the solar system by this definition of edge. After 35 years of travel, they had reached the membrane of the Great Bubble and passed through it. It is worth pausing to consider what these two machines are and what they are doing now, because there is something almost unbearably moving about it. The Voyagers are not large. Each one weighs less than a ton, about the weight of a small car. They were built with 1970s technology, with computers far less powerful than a modern pocket calculator, let alone the phone in your pocket. Their memories are measured in kilobytes. They were designed originally for a mission that was supposed to last only a few years, a tour of the outer planets, and instead they have flown on for nearly half a century, far beyond anything their builders dared to plan for. They carry instruments to measure particles and magnetic fields, cameras that have long since been switched off to save power, and a small nuclear power source that has been slowly fading ever since launch, its output dropping a little every year as the radioactive material inside it decays. They are running now on a tiny fraction of the power they had at the start. To keep going, engineers have been shutting down their instruments one by one, and even turning off the heaters that keep their remaining equipment warm, gambling that the hardware can survive in the deep cold longer than expected. So far, against all odds, it has. But the fading cannot be stopped. Within the next few years, perhaps by the early 2030s, the last of their instruments will fall silent and they will go dark. They will stop speaking to us. The longest conversation in the history of exploration, a conversation that has lasted nearly 50 years and crossed the edge of the solar system, will simply end, not with a failure or a disaster, but with the quiet running down of a battery in the dark. And after that, the Voyagers will keep flying. Long after we can no longer hear from them, long after everyone who built them is gone. They will continue outward, silent, into the space between the stars, carrying their instruments dead and their cameras blind, coasting on the same momentum that has carried them since 1977. Each Voyager also carries a record, a golden phonograph disc mounted on the side of the spacecraft containing sounds and images of Earth. There are greetings spoken in 55 languages, from ancient Akkadian to modern English. There is music from many cultures and eras, from Bach to Chuck Berry, from Javanese gamelan to the songs of indigenous peoples. There are the sounds of the natural world: wind, rain, thunder, the calls of birds and whales, the sound of a human heartbeat and a mother's first words to her newborn child. There are encoded photographs of people, places, and living things, a portrait of the planet and the species that made the spacecraft. The records were intended as a message, in the almost unimaginable event that one of the spacecraft is ever found, in the deep future, by some other intelligence among the stars. The chance of that happening is so small as to be almost meaningless. The Voyagers are not aimed at any particular star, and the distances between stars are so vast that the spacecraft will drift through the galaxy for an immensely long time without coming near anything. But the gesture matters, perhaps more for what it says about us than for any practical hope. We built 2 machines, sent them to study the planets, and when their work was done, we let them carry a portrait of our world outward, past the edge of the solar system, into a journey that will outlast not only the people who built them, but very likely the entire human species, and even the Earth itself. Billions of years from now, when the sun has swollen and the Earth is gone, the Voyagers, or what remains of them, may still be out there, drifting between the stars with their golden records intact, the last surviving trace of a world that no longer exists. They are the farthest traveled expression of our existence, and the most durable. So the heliopause gives us our third edge, and it is a powerful candidate, perhaps the most defensible of all. It is the boundary of the sun's physical presence, the place where the sun's own material ends and the material of the galaxy begins. It is the edge we have actually reached, the only one a human object has ever crossed. By this definition, the Voyagers have left the solar system, and the statement is true and meaningful. When people say that the Voyagers are in interstellar space, this is the boundary they mean, and they are right to say it. The sun's wind no longer reaches them. They are out in the gas of the galaxy, in the medium that lies between the stars, somewhere no human-made thing has ever been before. And yet, there is a fourth edge, far beyond this one, and by that definition, the Voyagers have not left the solar system at all. They have not even come close. They are, by this final measure, still deep within the sun's domain, and will be for many thousands of years to come. Because the sun holds more than just a bubble of wind. It holds, by its gravity, an enormous shell of distant icy worlds, so far away that the heliopause we have just crossed is, by comparison, practically next door, almost within arm's reach. To reach that final edge, We have to leave the Voyagers behind and travel onward into a region so remote, so cold, and so vast that no spacecraft we have ever built will reach it for tens of thousands of years. To find the last edge of the solar system, we have to change what we are measuring one more time. The first edge was marked by the planets, by the Sun's family of worlds. The second, by the icy bodies of the Kuiper Belt, the leftover building material of those worlds. The third, by the Sun's wind, the great bubble of the heliosphere. But there is one more way the Sun holds on to things, and it is the most far-reaching of all. It is gravity. And the Sun's gravity extends almost unimaginably farther than its light, its wind, or its planets. Light fades with distance. The solar wind runs out of force and stops at the heliopause. But gravity, though it weakens with distance, never truly stops. It reaches on, growing fainter but never vanishing, and far out in the dark, long past the point where the Sun's wind has died and its light has dwindled to a single bright star among many, the Sun's gravity is still strong enough to hold things in orbit. To find the place where that gravitational grip finally loosens, we have to travel outward from the heliopause, not a little farther, not twice as far, but more than 1,000 times as far. We are about to leave behind everything familiar, including the Voyagers, and journey into the most remote region the Sun can still call its own. This region is called the Oort Cloud, named after the Dutch astronomer Jan Oort, who proposed its existence in 1950. Oort was trying to solve a puzzle about comets. Comets are icy objects that fall in toward the Sun from the outer solar system, and as they approach, the Sun's heat boils the ice from their surfaces, releasing gas and dust that streams away into the long, glowing tails that have made comets objects of wonder and dread throughout human history. Some comets return regularly on predictable orbits of a few years or a few decades. Halley's Comet, the most famous of these, returns roughly every 76 years, close enough that a person might see it twice in a long lifetime. These short-period comets come from the Kuiper Belt, the region we have already visited, and their orbits lie more or less in the same flat plane as the planets. But there is another kind of comet, and it was these that puzzled Oort. The long-period comets appear suddenly, without warning, swing once around the Sun, and then vanish back into the dark on orbits so long that they will not return for thousands or tens of thousands, or even millions of years. Oort noticed two strange things about them. First, they did not come from the flat plane of the planets. They came from every direction in the sky, plunging in from above and below and all around, as if they were falling inward from a source that surrounded the solar system completely on every side. Second, when he calculated their orbits, he found that they were falling in from enormous distances far greater than anything then known, from somewhere thousands of times farther out than the planets. From these clues, Oort deduced something remarkable. There must be, he reasoned, a vast reservoir of icy bodies surrounding the entire solar system, not in a flat disk like the Kuiper Belt, but in a great hollow sphere, a shell enclosing the Sun and all its planets on every side at once. This shell would have to be immensely far away, and it would have to contain a staggering number of objects in order to supply the steady trickle of long-period comets that fall in toward the Sun across the ages. The objects in this shell would be so distant, so faint, and so slow-moving that they could never be seen directly with the telescopes of his time. Their existence could only be inferred from the comets they occasionally sent inward, like the existence of a distant unseen orchard inferred from the occasional apple that rolls down to your feet. This is the Oort Cloud. And here's the most striking fact about it. Even now, 3/4 of a century after Oort proposed it, it has never been directly observed. No telescope has ever photographed it. No object that clearly and certainly belongs to it has ever been seen in its distant home. We believe it is there, with great confidence, because of the comets that fall from it and because the calculations all point to it. But the outermost region of our own solar system, the region that defines its final edge, remains to this day a place we have inferred but never actually seen. It is the best established invisible thing in the solar system. The scale of the Oort Cloud is where the mind begins to fail, and it is worth slowing down to let the numbers land, because they are the whole point. We have been traveling outward this entire journey, and at each stage the distances have grown. The planets reach out a few billion kilometers. The Kuiper Belt, our second edge, extends to perhaps 50 times the Earth's distance from the Sun. The heliopause, our third edge, lies around 18 billion kilometers away, more than 90 times the Earth's distance from the Sun, and it took our fastest spacecraft 35 years to reach it. The Oort Cloud begins perhaps 1,000 times farther out than the heliopause, and it extends outward from there for an enormous span, its outer edge possibly lying as far as 100,000 times the distance from the Earth to the Sun. That is a distance of nearly 1.5 light years. To understand what that means, consider this. The nearest star to the Sun, a small red dwarf called Proxima Centauri, lies about 4 light years away. If the Oort Cloud reaches out to 1.5 light, then the Sun's gravitational territory extends more than 1/3 of the way to the nearest other star. The solar system, defined by gravity, is not a tidy disk of planets a few billion kilometers across. It is a vast sphere well over 2 light years in diameter, and the planets, the Kuiper Belt, and the entire heliosphere are crowded together in a tiny, bright knot at the very center of it, a knot so small by comparison that on a map of the whole solar system it would be invisible. A single dot, too fine to see. Almost the entire solar system, by volume, is the dark, cold, near-empty sphere of the Oort Cloud. Everything we have ever photographed, every world we have ever named, every place any spacecraft has ever been, fits inside a speck at the center of a structure that reaches out toward the neighboring stars. It is at this scale that the Voyagers, our faithful companions throughout this journey, finally fall behind. We have followed them across the heliopause, into interstellar space, to the farthest place any human object has ever reached. But they are nowhere near the Oort Cloud. At their current speed, that same 17 kilometers every second, it will take Voyager 1 about 300 years simply to reach the inner edge of the Oort Cloud, and then roughly 30,000 years more to pass all the way through it and emerge on the far side. 30,000 years. It is worth letting that number sit. The whole of recorded human history, from the first written words and the first cities to this present moment, spans only about 5,000 years. The cave paintings of Lascaux, among the oldest art our species has left, are around 17,000 years old. Our fastest spacecraft, our farthest traveled emissaries, the most distant objects we have ever made, will spend longer crossing this single region of our own solar system than the entire span of human art and history, twice over. And they will make that crossing in silence and darkness, their power long since gone, their instruments dead, their cameras blind, drifting through a shell of icy worlds they can no longer sense, and that we, on Earth, have never seen. By the time the Voyagers leave the Oort Cloud behind, our species may no longer exist. The languages on their golden records may be as dead as Akkadian. And still, they will drift on, carrying their portrait of a long-vanished world, only 1/3 of the way to the nearest star. This is the moment to feel the true size of the thing we live inside. We began this journey thinking the solar system might end at the last planet, a little under 4.5 billion kilometers from the Sun, the answer the 19th century would have given. The real outer edge, defined by the Sun's gravity, lies thousands of times farther out than that. Everything we normally think of as the solar system, the Sun and the planets, and even the great bubble of the heliosphere, occupies only the innermost speck of the Sun's actual domain. The vast majority of the solar system, by volume, is the dark, cold, almost empty sphere of the Oort Cloud. populated by an estimated trillions of icy bodies, each one drifting along an orbit that may take millions of years to complete, most of them never coming anywhere near the sun, never warming, never changing, simply circling in the dark at the very limit of the sun's reach. These are not small numbers of objects. There may be more comets in the Oort Cloud than there are stars in the galaxy. And yet the cloud is so vast that despite holding trillions of bodies, it is almost perfectly empty. The average distance between one Oort Cloud object and the next may be tens of millions of kilometers. An object out there could drift for centuries without ever passing close to another. In recent years, astronomers have begun to find objects that may be the first hints of this distant realm, the inner fringe of the Oort Cloud reaching down toward the regions we can observe. The most famous of these is a small world called Sedna, discovered in 2003 by the same Mike Brown, who would later find Eris. Sedna follows an extraordinary orbit, unlike almost anything else known. At its closest approach to the Sun, it is already far beyond the Kuiper Belt, in the cold and the dark. At its farthest, it travels hundreds of times the distance from the Earth to the Sun, out into the deep emptiness, before slowly falling back. A single orbit of Sedna takes around 11,000 years to complete. Think about what that means. When Sedna last came as close to the Sun as it is now, the last ice age was ending. Humans were just beginning to plant the first crops, to settle into the first villages, to take the first steps toward everything we now call civilization. Sedna has been traveling outward and back, once, in the time it has taken our species to go from the first farms to spacecraft and the internet. It will not return to this point again until a time as far in our future as the dawn of agriculture is in our past. And for almost the entire length of that 11,000-year journey, Sedna is out in the dark, far from the sun, invisible to us. We have caught it now only because it happens, at this particular moment in its enormous orbit, to be near the closest point it ever reaches. For most of its existence, a world like Sedna simply cannot be seen at all. There is one way, and only one way, that the Oort Cloud reaches into our lives and becomes visible to us. And it is the very thing that led Jan Oort to deduce its existence in the first place. Every so often, one of its trillions of icy bodies is nudged inward, falls toward the sun across an immense span of time, and arrives in the inner solar system as a comet, briefly blazing in our sky before vanishing again into the dark. When you see a great comet, you are looking at a visitor from the outermost edge of the solar system, a piece of the fourth boundary that has, after a journey of perhaps millions of years, come close enough to be seen with the naked eye. It is the only time the Oort Cloud ever shows itself. A comet is, in essence, a dirty snowball, a small body of ice and dust that has spent almost its entire existence frozen and inert in the deep cold far from the sun. For most of its life, it is utterly invisible, a dark lump of ice drifting through the outer solar system, no different from the countless others around it. But as it falls inward and the sun's warmth begins to reach it, something happens. The ice begins to turn directly to gas, streaming off the comet's surface and carrying dust with it, wrapping the small solid core in a glowing cloud of released material. This cloud, lit by the sun, is what makes a comet visible across the vast distances of the inner solar system. And as the comet nears the sun, the solar wind and the pressure of sunlight blow this released material outward into the long, luminous tail that has made comets objects of awe and terror throughout human history. The tail can stretch for tens of millions of kilometers, longer than the distance from the sun to the Earth, a vast banner of glowing gas and dust unfurled across the sky. One detail about that tail reveals something beautiful about how the solar system works. A comet's tail does not stream out behind it the way smoke trails behind a moving train. Instead, it always points away from the sun, regardless of which way the comet is traveling. As the comet falls inward, the tail trails behind it. But as the comet rounds the sun and heads back out, the tail swings around and streams ahead of it, pushed always outward, away from the sun, by the relentless pressure of sunlight and the solar wind. The tail is not a trail of exhaust. It is a windsock, showing the direction of the sun's outflowing wind and light, the very same solar wind that carves out the heliosphere far beyond. In the glowing tail of a comet, we are seeing the solar wind made visible a second time, just as we see it in the aurora, but now out among the planets, blowing the breath of a frozen visitor back toward the dark it came from. Some comets have become part of human memory. Hale-Bopp, which blazed in the sky through much of 1997, was one of the brightest and most widely seen comets of the 20th century, visible to the naked eye for a record 18 months, hanging in the evening sky for so long that hundreds of millions of people saw it. It will not return for thousands of years. More recently, in the summer of 2020, a comet known as Neowise swept through the inner solar system and became a lovely sight in the northern sky, photographed by countless people during a year when much of the world was looking for reasons to step outside and look up. Comets like these are not from the Oort Cloud's farthest reaches in every case, and tracing exactly where each one originates is difficult, but the long-period comets, the ones that take thousands or tens of thousands of years to return, are the Oort Cloud's emissaries, falling in from distances that beggar the imagination, briefly visiting the warm inner solar system before climbing back out into the cold for another age. There is something quietly profound in this. The Oort Cloud, the most distant and least understood region of our solar system, the one we have never photographed and never directly seen, nonetheless sends us messengers. Across human history, every culture that ever watched the sky has seen comets, and most of them, not knowing what comets were, read them as omens, as signs of disaster or change, as visitors from the realm of the gods. They were closer to the truth than they knew. The comets were visitors, not from the realm of the gods, but from the farthest edge of the sun's domain, falling inward from a region so remote that the comet's journey to reach our sky may have taken longer than the entire history of the human species. When a comet appears, the outermost solar system has reached down and touched the innermost, and for a few weeks, a fragment of the fourth edge hangs in our sky, glowing before it returns to the dark. For a span of time we can barely comprehend. Every comet is a brief, rare conversation between the edge of the solar system and its heart. A handful of other objects on similar extreme orbits have since been found, and together they form a category sometimes called the detached objects, because their orbits are detached from the influence of the planets, reaching out into the region between the Kuiper Belt and the Oort Cloud, a region we are only beginning to explore. These objects are mysterious. Their orbits are difficult to explain by any process we fully understand. And here the story takes a genuinely strange turn. Several of these distant objects have orbits that seem to be tilted and clustered in a similar way, as though something were hurting them, as though some unseen gravitational influence were shepherding them onto aligned paths. Some astronomers, including Mike Brown again, have suggested that the most natural explanation for this clustering is the gravity of an undiscovered planet, far out in the darkness beyond the Kuiper Belt, a world perhaps 5 to 10 times the mass of the Earth, orbiting the Sun at a tremendous distance, taking thousands of years to complete a single circuit. This hypothetical world has been given a name. It is called Planet 9. Planet 9 has never been seen. Its existence is inferred, controversially, from the orbits of a handful of distant objects, and not all astronomers are convinced. Some argue that the apparent clustering is an illusion, a product of the difficult and incomplete way we have surveyed the outer solar system, a pattern that may dissolve as we find more objects. The debate is active and unresolved, but consider what it means that the debate can happen at all. Serious astronomers, using the best instruments available, can propose that an entire planet larger than the Earth is orbiting the Sun in the outer solar system, and they cannot easily prove it wrong. And they cannot easily find it, because the region where it would be is so vast, so dark, and so distant that even a whole planet could be lost in it. A world several times the size of Earth could be out there right now, part of our own solar system, and we would struggle to see it. That is how little we know about these remote regions. That is how big and how dark the outer solar system truly is. This is the strange truth the Oort Cloud leaves us with. The outermost region of our own solar system, the place that defines its true gravitational edge, is a region we have never seen, populated by objects we can only infer, possibly containing worlds we have not discovered, extending out toward distances that begin to overlap with the territory of other stars. And out there, at the very limit, the Sun's gravity does not stop at a clean line. It simply weakens gradually, until at some point, more than a light year away, the faint pull of a passing star becomes as strong as the Sun's, and an icy body drifting at that distance no longer clearly belongs to one star or the other. The boundary between our solar system and the next is not a line drawn in space. It is a region of gradual surrender, a zone where the Sun's hold becomes so gentle that the gravity of other stars can reach in and pull objects away, or push them inward, or simply share them. Every so often, a passing star drifts close enough to the Sun over millions of years to disturb the Oort Cloud, jostling its distant residents, sending some of them falling inward toward the Sun to become the long-period comets that puzzled Jan Oort, and flinging others away into interstellar space entirely, lost from the Sun forever. The edge of the solar system, out here, is porous. Things drift across it in both directions. It is less a border than a tide line, where two oceans meet and mingle, and neither fully owns the water. That image of a passing star disturbing the Oort Cloud is not merely theoretical, and it is not only something that has happened in the distant past. It is something we can see coming. Astronomers, by carefully tracking the motions of nearby stars, can predict which ones will pass close to the Sun in the future. And the answer is that stars pass by surprisingly often, on the timescales of the solar system. Roughly every few 100,000 years, some star drifts close enough to brush the outer fringes of the Oort Cloud. Most of these passages are distant and gentle, but occasionally one comes closer, and we know of one that will. A small dim red star called Gliese 710, currently about 60 light-years away in the constellation of Serpens, is heading more or less straight toward us. It will not hit us. The distances involved are far too vast for any real danger of collision. But in roughly 1.25 million years, Gliese 710 will pass through the outer reaches of the Sun's Oort Cloud. Closer than any known star will come in that span of time, sweeping through the distant shell of comets on the very edge of the Sun's gravitational domain. When it does, its gravity will stir the cloud, nudging some of the icy bodies out there onto new paths. Some will be flung away into interstellar space, lost to the Sun forever. Others will be knocked inward, sent falling toward the inner solar system to become comets, arriving over the following hundreds of thousands of years as a slow, faint increase in the number of comets crossing our sky. Astronomers call this a comet shower, although it is nothing so dramatic as the word suggests, just a gentle rise in the comet rate, spread across an enormous span of time. By the time those comets arrive, our species, if it still exists in any form, will be as different from us as we are from our most distant ancestors. But the comets will come, sent on their way by a star that at this moment is still a distant point of light far out in Serpens, drifting slowly toward an appointment with the edge of our solar system more than 1 million years from now. This is the deep rhythm of the outer solar system, far slower than anything in human experience, but real and ongoing. Stars pass. The Oort Cloud is stirred. Comets fall inward. Some of the cloud is lost, flung into the dark, and some is exchanged. For when a star passes through our Oort cloud, our sun in turn passes through the outer fringes of whatever cloud that star may carry, and the two systems may quietly trade a few of their most distant, most loosely held members in the encounter. Over the long history of the galaxy, this has happened countless times. The sun has passed near many stars, and many stars have passed near the sun, each encounter gently reshaping the outer cloud, scattering some of its members, capturing perhaps a few new ones. Some of the objects in the Oort cloud today may not have formed around our sun at all, but may have been captured from other stars during these slow, ancient passages, so that our solar system's outermost shell could be a mixture, partly our own and partly inherited from stellar neighbors we passed in the deep past and will never see again. And in the very long run, the Oort cloud will not last forever. The sun's gravitational grip on these most distant objects is so faint that over billions of years, the cumulative effect of passing stars and the gentle tug of the galaxy itself will slowly strip the cloud away, object by object, across spans of time that dwarf even the age of the solar system so far. The Oort cloud will erode, its members scattered into the galaxy, until eventually the sun's outermost shell thins toward nothing. This will not happen soon. It will not happen for billions of years, and long before it is complete, the sun itself will have changed. In about 5 billion years, the sun will exhaust the fuel at its core, swell into a vast red giant, and then collapse into a slowly cooling ember, a white dwarf, no longer the warm yellow star we know. Its gravitational reach will weaken as it sheds its outer layers, loosening its hold on the Oort cloud still further. The planets that survive will drift into wider orbits, and the great shell of comets, already thinning, will loosen and disperse into the galaxy, mingling at last and completely with the space between the stars from which it was never fully separate. So the fourth edge of the solar system is not only the most distant and the most uncertain, it is also the most temporary. The planets are stable. The sun will shine for billions of years yet. But the outermost edge of the solar system, the faint sphere of the Oort cloud, is a slowly dissolving thing, eroding at its fringes with every star that passes, destined in the deep future to fade into the galaxy entirely. The edge of the solar system, by its farthest definition, is not a fixed boundary that has always been there and always will be. It is a structure with a history and a future, gathered slowly in the solar system's youth, stirred and traded across billions of years of stellar encounters, and fated, in the end, to come undone. Even the edge of everything, it turns out, is passing. Even the boundary is on a journey of its own. So this is our fourth edge, and the most distant of all. Not a wall, not a shock, not a membrane, but a slow fading of the sun's gravitational grip across an enormous invisible sphere, ending more than a third of the way to the nearest star. By this definition, the solar system is unimaginably larger than the familiar picture, and the Voyagers, for all their traveling, have barely left the front doorstep. And it raises one final question, the question we will turn to next. If the edge of our solar system reaches a third of the way to the next star, and that star has an edge of its own reaching back toward us, then what really lies in the space between? What fills the gap between the stars, and what wanders through it? Because the boundary we have just reached is not only the edge of our solar system, it is the beginning of everything beyond. If the edge of our solar system reaches out toward the neighboring stars, and their edges reach back toward us, then the obvious question is what lies in between, and whether anything ever crosses the gap. For most of history, this was a purely theoretical question. The space between the stars seemed impossibly remote, a void that nothing from outside could ever traverse to reach us, and nothing of ours could ever cross to reach them. But in the last decade, that changed. We discovered for the first time objects that did not belong to our solar system at all, visitors from around other stars, passing through our neighborhood on their way to somewhere else. And their arrival gave us our first direct, physical contact with the material of other star systems. The first of them appeared in October of 2017. Astronomers using a survey telescope in Hawaii, scanning the sky for near-Earth asteroids, noticed an object moving in a way that made no sense for anything belonging to the Sun. It was traveling far too fast, on a path far too steeply angled, to be a normal asteroid or comet. When they calculated its orbit, the answer was startling. The object was not on a closed orbit around the Sun at all. It was on a path that came in from interstellar space, swung once around the Sun, and was already heading back out, never to return. It had not come from our solar system. It had come from somewhere else, from around another star, and it was just passing through. It was the first object from beyond our solar system that humanity had ever detected inside it. They named it Oumuamua, a Hawaiian word meaning roughly a scout or messenger from the distant past, one who reaches out. The name was apt because that is exactly what it was. A piece of another star system, arriving at ours after an immense journey through the dark. By the time it was discovered, Oumuamua had already rounded the Sun and was on its way out, fading fast, and astronomers had only a few weeks to study it before it became too distant to see. What they found in those few weeks was deeply strange. Oumuamua was small, only a few hundred meters across, and it appeared to be extraordinarily elongated, far longer than it was wide, possibly shaped like a cigar, or by some interpretations, like a flat disk. Nothing quite like it had been seen before. It tumbled as it went, its brightness flickering dramatically as its odd shape turned different faces toward us. And as it departed, it seemed to speed up slightly, accelerating in a way that could not be fully explained by the Sun's gravity alone. That small unexplained acceleration set off a great deal of speculation. For comets, such an effect is normal and well understood. As a comet warms near the Sun, jets of gas erupt from its surface and give it a gentle push, like a slow leak from a balloon nudging it along. But Oumuamua showed no visible signs of being a comet. It had no tail, no glowing cloud of gas and dust around it. So what was pushing it? Most astronomers concluded that it was probably venting gas in some way too faint to see, an unusual comet of a kind we had simply never encountered before, perhaps made of ices that release no visible dust. A small number of scientists wondered, more controversially, whether the object's strange shape and motion could indicate something artificial, a fragment of technology from another civilization, perhaps a kind of light sail pushed by sunlight. This idea captured the public imagination, but it remains very much a minority view, and the evidence does not require it. The most likely explanation is that Oumuamua was a natural object, a piece of another solar system, but one of a type we had never seen up close, behaving in ways we did not fully expect. The truth is that we will probably never know for certain. It is gone now, receding into the dark, and we got only a single, hurried look before it left. What matters most about Oumuamua is not its peculiar shape or its mysterious acceleration. It is the simple, profound fact of its existence. Here was an object that had formed around another star, been flung out of its own system at some point in the deep past, perhaps billions of years ago, and had then drifted through interstellar space for an unimaginably long time before happening to pass through our solar system, where for a few weeks we saw it. It was a physical piece of another star system, and it came to us. We did not have to travel to the stars to touch the material of another world. A fragment of one came to us on its own, carried by the slow currents of the galaxy. And it was not the only one. In August of 2019, less than 2 years later, an amateur astronomer named Gennady Borisov, observing from Crimea with a telescope he had built himself, discovered a second interstellar visitor. This one, named Borisov in his honor, was unmistakably a comet. It had a clear tail, a glowing coma of gas and dust, all the familiar features of a comet from our own solar system, except that it too was on an unbound path, coming in from interstellar space and heading back out. Borisov was, in a sense, more reassuring than Oumuamua. It looked like a normal comet. It behaved like a normal comet. The only difference was that it had come from around another star. Its composition, when astronomers analyzed the light from its tail, was broadly similar to comets from our own system, with some intriguing differences, suggesting that the basic chemistry of comet formation is much the same around other stars as it is around ours. Where Oumuamua had been a baffling oddity, Borisov was a familiar object with an unfamiliar origin, and together the two of them told us something important. Interstellar visitors come in more than one kind, and they are passing through more often than we had realized. The discovery of these two objects, so close together in time, told astronomers that the space between the stars is not as empty of wanderers as it might seem. If we detected two interstellar visitors in the span of 2 years, once we finally had telescopes capable of spotting them, then there must be a great many more passing through the solar system all the time, most of them too small or too faint or too fast to notice. The galaxy, it turns out, is full of these drifting objects, castaways flung out of their home systems, wandering the dark between the stars for billions of years, occasionally passing through the territory of another sun. Our own solar system has almost certainly thrown out vast numbers of its own, comets and icy bodies flung outward by the gravity of the giant planets in the chaotic early days, or jostled loose from the Oort Cloud by passing stars. Somewhere out there, fragments of our solar system are drifting through other star systems, and perhaps, around some distant star, an astronomer of another kind has noticed one of them passing through, a scout from a star they will never visit, carrying no message but real and ours. This is what the space between the stars is really like. It is not a perfect, sterile vacuum with the stars as isolated islands separated by absolute nothing. It is a vast, thin medium, sparsely populated, through which objects drift on journeys lasting millions or billions of years. There is gas between the stars, extremely thin, sometimes gathered into great clouds light years across, the same kind of clouds from which new stars are born. There is dust. There are these wandering objects, the interstellar castaways, and there are, no doubt, the distant fringes of other stars' versions of the Oort Cloud, reaching out toward ours, so that in the depths between the stars, the gravitational territories of neighboring suns may gently overlap, their outermost icy bodies mingling in a shared and ownerless dark. The next nearest star, Proxima Centauri, lies about 4 light-years away. That distance is so vast that if the Sun and Proxima Centauri were each shrunk to the size of a grain of sand, the two grains would be separated by something like 60 kilometers of empty space, with almost nothing in between. This is the true emptiness of the galaxy. The stars are not crowded together like lights in a city. They are scattered like a handful of sand grains across an entire country. And yet, even across that emptiness, objects travel. Oumuamua crossed it. Borisov crossed it. The Voyagers are crossing it now, slowly, and will go on crossing it for tens of thousands of years. The space between the stars is almost unimaginably empty, and almost unimaginably vast. And still, somehow, things move through it, carried by gravity and momentum on journeys that began before our species existed, and will end long after it is gone. It is worth holding both of these truths at once, because together they capture something essential about the scale of the cosmos. The galaxy is mostly empty, emptier than any emptiness we can intuitively grasp, and the galaxy is also connected threaded with slow, patient motion, with objects drifting from star to star across spans of time that dwarf all of human history. Our solar system is not a sealed and isolated bubble. Its outermost edge blends into the wider galaxy, exchanges material with it, receives the occasional visitor from it, and sends its own castaways out into it. The edge of the solar system, by the time we reach its farthest definition, is not really an edge at all. It is a threshold, a place where our small bright region of the galaxy fades gradually into the immense dark expanse of everything else. We set out at the beginning of this journey with a simple question: where does the solar system end? And we have found, as promised, not one answer but four, each of them real, each of them defended by serious people, each of them marking a genuine boundary of a different kind. It is worth gathering them together now, one last time, to see the whole shape of the thing we have traveled through. The first edge is the orbit of the last planet, Neptune, a little under 4.5 billion kilometers from the Sun. This is the edge of the Sun's family of major worlds, the boundary the 19th century would have given, the edge that fits on the old diagrams. It is real. Past Neptune, there are no more major planets. But it is also the nearest and the least of the edges, because the solar system, as we have seen, does not stop there at all. The second edge is the outer limit of the Kuiper Belt, the broad ring of frozen worlds that begins at Neptune and extends outward to perhaps 50 times the Earth's distance from the Sun, before falling away at the Kuiper Cliff. This is the edge of the solar system's solid leftover material, the boundary of the disk of debris from which the planets were built. It is home to Pluto and Eris, and a whole population of icy worlds we did not even know existed a single human lifetime ago. It is farther out than the first edge, and it represents a different kind of boundary. Not the edge of the planets, but the edge of the planet-forming disk. The third edge is the heliopause, the membrane of the great bubble blown by the solar wind, lying around 90 times the Earth's distance from the Sun, more than 4 times farther than Neptune. This is the edge of the Sun's physical presence, the boundary of the region filled with the Sun's own material, the place where the solar wind dies and the gas of interstellar space begins. It is the only one of the 4 edges that a human-made object has ever crossed. When the Voyagers passed through it in 2012 and 2018, they became the first things we have ever built to leave the Sun's domain by this definition, and to enter the space between the stars. And the fourth edge is the outer boundary of the Oort Cloud, the vast spherical shell of comets held by the Sun's gravity, reaching out perhaps 100,000 times the Earth's distance from the Sun, nearly a light and a half, more than a third of the way to the nearest star. This is the edge of the Sun's gravitational reach, the most distant boundary of all, so far away that everything else we have visited, all the planets, the whole Kuiper Belt, the entire heliosphere, fits in a tiny bright speck at its center. This is the edge that the Voyagers will not reach for 30,000 years, the edge that defines the true and total extent of our solar system, and the edge that fades, at its limit, into the territory of other stars. 4 edges, then, nested one outside the next, separated by enormous distances, each one a true boundary of a different kind. Which of them is the real edge of the solar system? The honest answer is that the question does not have a single correct answer, and that this is not a failure of science, but a feature of reality. The solar system does not have a sharp edge, because the Sun does not hold on to things in a single way. It holds them with light, with wind, and with gravity, and each of those reaches a different distance. To ask where the solar system ends is to ask which kind of influence we mean, and depending on the answer, the boundary lies in one of 4 very different places. The edge is not a line. It is a series of fadings, a gradual loosening of the Sun's grip, played out across distances so vast that light itself takes hours, and then days, and then more than a year, to cross them. There is something fitting about this, and something worth carrying away from the whole journey. We are used to thinking of things as having clear boundaries, sharp edges, definite ends. A room ends at its walls. A country ends at its border. A coastline divides the land from the sea. But the universe, on its largest scales, does not work this way. It prefers gradients to lines, fadings to walls, transitions to thresholds. The solar system does not stop. It thins, it loosens. It fades outward through layer after layer, each one fainter than the last, until at some point so far away that no spacecraft we have built will reach it for tens of thousands of years. The sun's hold becomes so gentle that the next star's pull is just as strong, and our solar system quietly becomes the space between the stars. Consider one last time the scale of what we have traveled through, because it is the kind of thing the mind can hold only briefly before it slips away, and it is worth holding for as long as we can. We live on a small rocky world, third from the sun, in the warm and crowded inner reaches of the solar system. From here, the sun is a fierce and dominating presence, the source of all our warmth and light and life. But our world, and everything we have ever known, occupies only the innermost speck of the sun's true domain. Beyond us lie the giant planets, each in its own vast territory. Beyond them lies the Kuiper Belt, the frozen archive of the solar system's birth. Beyond that lies the edge of the sun's wind, the membrane of the heliosphere, which our two Voyagers have only just crossed after half a century of flight. And beyond even that, 1,000 times farther still, lies the great dark sphere of the Oort Cloud, reaching out toward the neighboring stars, holding trillions of icy worlds in a silence and a cold and a distance that the human mind can name but cannot truly feel. And through all of it, the Voyagers are still flying. Right now, as you finish watching this, those two machines are out there in the dark, the nearest one more than 24 billion kilometers away, still sending back their faint signals across the more than 22 hours it takes their voices to reach us. They have crossed the heliopause. They are in interstellar space, by the definition that boundary provides. And they are still, by the measure of the Oort Cloud, deep inside the solar system, with 30,000 years of traveling ahead of them before they pass its outermost edge. Both of these things are true at once. And in that double truth lies the whole strange answer to the question we began with. The Voyagers have left the solar system, and the Voyagers have barely begun to leave it. The edge is behind them, and the edge is impossibly far ahead. It depends, as it always has, on which edge you mean. Within a few years, the Voyagers will fall silent. Their power will fade past the point where they can speak to us, and the long conversation will end. But they will keep going. They will cross the inner edge of the Oort Cloud in about 300 years, in silence. They will spend 30,000 years among its frozen worlds, in silence. And then, at last, they will pass beyond the farthest edge of the solar system, beyond the reach of the sun's gravity, fully and finally out, into the open galaxy. No human being alive today will know when it happens. No instrument will record it. There will be no signal, no marker, no moment of arrival, just as there was no wall at any of the other edges. There will only be a small, dark, silent machine built by a species that may no longer exist, drifting across an invisible threshold somewhere in the deep between the stars, carrying a golden record of a pale blue world, outward into everything else. That is what is really at the edge of our solar system. Not a wall and not an ending, but a long, gradual fading of the sun's reach, layer beyond layer, out into a darkness that is not empty but vast. Not a border, but a threshold. Not the end of everything, but the beginning of all the rest. The solar system does not stop. It simply becomes the universe. It is worth asking, at the end of a journey like this, why any of it matters. The edge of the solar system is not a place any of us will ever visit. It is not somewhere our descendants are likely to settle, not for a very long time, if ever. The nearest of its boundaries is years of travel away, even at the fastest speeds we can achieve, and the farthest is a journey of tens of thousands of years. Knowing where the solar system ends changes nothing about daily life. No crop grows differently, no tide turns, no morning arrives sooner or later, for our knowing that the Oort Cloud reaches a third of the way to the next star. And yet it matters, in the way that knowing our true situation always matters. For most of human history, we lived inside a small and cozy picture of the cosmos. The Earth was the center. The sky was a dome. The stars were lights fixed to it, and the whole arrangement was built around us, close and comprehensible, and within reach. One by one, that picture has been taken apart. We learned that the Earth goes around the Sun, not the other way round. We learned that the Sun is one ordinary star among hundreds of billions. We learned that our galaxy is one among trillions. And we have learned, as this journey has shown, that even our own solar system, the one small region we might have called home, is far larger and stranger and emptier than we ever imagined, that it has no single edge, that it fades outward through layer after layer into a darkness that reaches most of the way to the neighboring stars. Each of these discoveries has made us smaller. Each has moved us further from the center, and yet each has also enlarged us. Because to know the true size of the thing you live inside is to become, in some sense, large enough to hold it in your mind. That perhaps is what is really at the edge of our solar system. Not just ice and comets and the fading wind of the sun, but a measure of how far our understanding can reach. We cannot travel to the Oort Cloud. We cannot photograph it. We may never touch a single one of its trillions of worlds, but we have worked out that it is there. We have traced the four edges of our solar system from our small blue world near the center, using nothing but light, mathematics, patience, and two fading spacecraft built half a century ago. We have mapped a structure that stretches 2 light years across, most of which no eye will ever see, simply by thinking carefully about the things we can observe. The edge of the solar system lies impossibly far away in the cold and the dark. But it is not beyond us. We have already, in the only way that truly counts, been there. If you found this journey to the edge of the solar system worthwhile, a like or a subscribe helps us keep making them. There is a great deal more out there, in the dark beyond the planets, and we will keep traveling toward it, one edge at a time,